Welcome to part 3 of matrix multiplication. So one thing to keep in mind is that, as is the message here, is that matrix multiplication is not commutative. Um, Unlike with scalars, scalars, I don't know, 5 times 2, right? That would be the same as if you do 2 times 5. This is the property we call commutativity, right? And they, doesn't matter in which order you multiply these factors, they will be equal to the same number. But matrices, multiplication of matrices, we've seen that this operation is defined under some strict constraints or requirements, right? So there's a requirement about the number of columns in one matrix versus the number of rows on the other matrix. And at some point, in some level, matrix multiplication reduces to linear combinations of columns, linear combinations of vectors. So this is not as straightforward or trivial as, trivial if you will, as multiplication of scalars. Okay, so one thing to keep in mind is that this operation is not commutative. And so here we visit an example. We have matrices A and B. Both of these matrices are matrices with 2 rows and 2 columns. So A is 2 by 2, B is 2 by 2, and therefore they meet the requirements. We can multiply A times B, okay? We can multiply A times B, and we also can find B times A. So we can do the multiplication where this matrix is on the left side and B is on the right side, and then we can switch the order. In either case, we would be doing a 2 by 2 multiplying 2 by 2, and so that means that this number of columns of the matrix on the left matches the number of rows of the matrix on the right, and the dimensions of the new matrix are also 2 by 2, right? Because is the number of rows of A and the number of columns of B. So the end result would be A times B is a matrix that's also 2 by 2. But notice that this matrix has columns 19 and 6 in the first column, 3 and 2 in the second column. And if we multiply B times A, okay, we multiply B times A, we obtain a matrix that is not the same, right? So this, you can compare this column 1 is not the column 1 that we have in that other matrix over there. So therefore it's clear that A times B, this illustrates that the multiplication A times B is not equal to the multiplication B times A. So this, what's stated here as a theorem is actually the way in which many textbooks define matrix multiplication. And we have clarified that we're thinking of a matrix, okay, multiplying. So the main requirement is that this number of columns matches this number of rows, and so let's say that that multiplies another matrix that looks like this, right? And so we have defined this product, so this being A, as something that is like an operation that's continuously distributed, not continuous, but distributing the matrix column vector multiplication A times B1, A times B2, and so on, right? So this will go all the way to A times B sub P. Okay, this is how we think of this operation. So this being the first column and this being the second column and so on. But it turns out that we can think, if it's well defined, we can think of A, B, right? This as a completely new matrix, say it's a matrix C. Well defined and everything. So let's say that this is what we're calling C. Okay. Now let's take a look at one entry of C. So say the entry I sub the entry IJ. Okay, this means row I, column J. Well, that ij entry of the matrix product AB, that can be thought um, in the following way. It can be thought as if you involve row I of A and involve column J of B. Okay, so look at these numbers. This is AI1, this is AI2, this is AI3. Okay, this is all the way through AIN, and each of them is multiplying a number on the jth column of the matrix that's on the right side of the product, right? So here is B1 sub j, B2 sub j, B3 sub j, and at the very end Bn sub j. Okay, so we can also visualize um, this sum here such that every term in the sum comes out from involving, just think of this entry, the ij entry of the product. Think of that coming out of something that looks like a row and a column, right? So you may argue this looks a little bit like a T. It has the shape of a T, right? So here is the row, here is the column, and we're involving the first entry here with the first entry over there. That's this. These two are the first term on that sum, and then we move on to the next entry on the row and the next entry on the column, and then they come together to form the second term in that sum, and that goes all the way to the last term in that row. So remember, the matrix A has n columns, so this last term is going to have index, the column number is going to be n at the very end, right? And that is matched, then this column of B has n entries, because that's one of the requirements to do the matrix multiplication. So this last entry is going to have an index involving n sub j, right? That's precisely what appears here in the last term of that sum. So this sum should remind you a little bit of inner products, okay? Inner products, a little bit. I'll bring this maybe later. But so with this definition, this is a way of referring to the ij entry of a matrix product. And as I said, in many textbooks, that is actually the definition of matrix multiplication. So we can take a look at these two matrices, check the dimensions. So is it possible to multiply them? Well, matrix A has 3 rows and it has 5 columns. Matrix B has 5 rows and it has 4 columns. So the product AB, A on the left, B on the right, we're talking about a 3 by 5 multiplying a 5 by 4. Okay, these two numbers match. That's what we want. So think of them matching. And then what is left, this product, say that AB equals C, then what is left are the number of rows of A and the number of columns of B. So we would say that the product, say C, is a 3 by 4 matrix. Okay, the new matrix C is a 3 by 4. And let's suppose that we're looking at row 2, column 3. So row 2, column 3, let's say that we're referring to C 2, 3, also AB, the matrix product AB, column row 2, column 3. Okay, that means that we would take a look at row 2 and we take a look at column 3, and we will form that sum, right? So this is 0 times 2. The first term in that sum would be 0 times 2. The second term, the sum, would involve negative 4 and 3. The next term is going to involve 1 and 2. So that'll be 1 multiplying 2. The next term involves 2 and -1. That would be 2 and -1. And then the last term is 3 times 0. Okay, 3 times 0. So if we did that, add up all these numbers, that would give us the number that's located on row 2, column 3 of the matrix product. Right, so writing this in a much nicer way with the proper notation. This is what I was referring to in the previous slide as Z sub 23, right? And that's the product AB, and that 2, you could say that's 23, but it's row 2, column 3. That's precisely the type of product we have, and then we see that that sum equals -3. Okay, so one way, if you only need specific entries of the product, then you could go and apply this definition or this theorem, if you will. But you could also compute the matrix product as we had defined, previously defined with linear combinations of columns, and then you could just take a look at the position, specific position you're interested in.